Hello everybody, this is Cameron Snow with Danomics.com. So in this video we're going to be talking about porosity, and we are going to start off by doing a little bit of review on the theory of calculating porosity, and then we're going to move into the hands-on portion of the video. So when it comes to porosity, this is one of the most important reservoir properties. So before you start to do a porosity calculation, there are some things that you should have already done. You should have already done your clay volume interpretation. You should have already done your TOC interpretation. And it's not until you get those done that you should move on to porosity. And the reasons for that will become evident as we start to go through the video, especially the hands-on portion of the video. So what's the objective of doing a porosity calculation? Well, porosity is the pore space within a rock, so that is where the oil and gas and water essentially is stored, and so obviously that is an important property for calculating our in-place volumes. How much oil, gas, or water is a rock capable of storing? And this has implications for a number of things. So obviously the biggest implication is just understanding how much oil is in place. But also if you think about the fact that porosity, is such a strong determinant of oil in place, then if you look at how much oil a well has recovered, porosity has a big impact on how you calculate recovery factor. And so if your expectations of porosity are off, then your understanding of recovery factor is off, and then that's really going to affect your operations in the field. So that's why it's so important to get your porosity calculated and calculated correctly. Once we calculate porosity, then we're going to apply some corrections, and two of those corrections are going from a total porosity to an effective porosity, and then applying a TOC correction for intervals that may have high TOC. And as always, one of the things that's key to setting up your model is calibrating to core, and so it really helps if you have core data, and that's something that we measure quite regularly, and it will help you understand, are you measuring a total porosity or an effective porosity, how close are those together, etc. So and there has been quite a shift in my career where people have gone from talking about effective porosities to almost exclusively working with total porosities, and that's been a result of starting to work with tighter reservoirs and higher shell content reservoirs. In terms of porosity methods, there are a lot of methods to calculate porosity, but there's three variants that you'll see that are very common, and these are the density porosity, the neutron density porosity, and the sonic porosity. So with density porosity, the thing here is that as you fill the pore space with fluid that has a lower density than the matrix, that results in a lower bulk density value on the log. So that's how you read a porosity log or a density porosity log. On a neutron density porosity log, you are looking at the density porosity, but you're also simultaneously looking at the neutron porosity. And neutron logs measure the amount of hydrogen in a formation, which is of course concentrated in the fluid-filled pore space. So hydrogen, H2O, hydrogen, hydrocarbons. So that's what the neutron porosity is measuring. And then sonic porosity, of course, is looking at interval transit time, in the rock, and obviously fluid-filled pore space has a higher interval transit time than non-fluid-filled matrix. In terms of the formulas, they are generally quite simple, at least from an introductory point of view. And so, if we think about a density porosity, what is it we're looking at? There's three variables here. We have our porosity is equal to our matrix density minus our the bulk density log values divided by our matrix density minus our fluid density. So the matrix density, what type of rock is it? Is it a sandstone? Is it a limestone? You set that matrix density accordingly. For the row fluid, a lot of people just default to a value of 1 for this because that's what the fluid density would be in a freshwater system, although you can be more sophisticated with that. And then the bulk density, that's the value that we measure in the logs. Then we expand on that and we get a neutron density method. Like I said, this is really two separate porosity methods. And you have people that will combine them in different ways. You can take a straight up average of the two. You can take a geometric mean of the two. You can take some weighted average. So it's a lot of people will take the neutron porosity plus twice the density porosity and then average that out. So that is how you go about that. And then in the sonic porosity, so there are different forms of this equation, but this is the Ramer-Hunt-Gardner method. This is the Wiley method, where it's very similar to the density porosity equation, but also takes into account a compaction factor for your shell. And like I said, there are alternative forms there to varying degrees of sophistication. So those are the three basic methods. There are a lot of variants on that that are specifically grain density based methods. We're going to talk about those when we go into the inversion. So let's just put those on hold for a second. And now let's go over to the hands-on part of the curriculum. I just want to give you a brief explanation and show you a few things to watch out for. So when we were looking at those equations, those were all equations to calculate a total porosity. So let's start off. We're going to look at this this interval right through here. So this is the teapot. We see an area where we have relatively clean gamma ray, higher resistivity, the neutron density are coming together. So this is a sandy portion of our interval, and we want to calculate the porosity here. What we do is we'd say, okay, well, I've done my geological homework. I know this is a predominantly quartz sand system with a lot of shells in it. So I come here and I set my matrix density parameter to be roughly 2.65. And then I apply that density porosity equation and I calculate a total porosity. And then if, depending on the type of analysis you're doing, you may want to correct that total porosity down to an effective porosity, which strips out the porosity that's attributable to the clays. And so we put in this clay porosity parameter. General values for that are between 10 and 15% for the clay porosity, although that is something that is it's a bit difficult to calibrate because the question is, how do you really measure porosity within the clay fraction? That's really not something you can measure in the lab very easily. So that is the clay porosity, and you can see here, so here in a shalier interval below our sand here, we see that our total porosity isn't that different, but then we see here our effective porosity, we really correct that down to significantly lower values, with the gray shading being the fraction of the porosity that we're attributing to the clay volume when we do that correction. The other thing that I mentioned was the TOC correction on the porosity. So if we go down to something like the Niobrara Formation, And if you remember when we did our calculation of TOC, we only had around 2% TOC, so not a huge amount. But if I toggle this off, and then if you paid close attention there, you did see a slight shift to the right, so to higher porosity. And if I turn that on, we are correcting that to lower porosity values. So what's happening there is, if you think about the Niobrara, we essentially said this is a limestone matrix, so it's got a matrix value of about 2.71, but that doesn't take into account that there is kerogen in there. And so, if we need to if we need to take that into account for the bulk density, what we need to do is adjust our bulk density to include that kerogen. So that is why we perform a TOC correction. Now, in 1-2% TOC, portions of the reservoir, this is not going to make a big difference. But if you start to deal with 5, 6, 8, 10% TOC, you are going to see a really noticeable difference when you do a TOC correction. So that is a calculation of porosity, as well as doing the total to effective correction and the TOC correction. I do want to show you a couple of things here. So let me go back up to this shallow interval where we have our sand shell system here. So I just want you to pay attention as I move from a density porosity to a neutron density porosity. What you'll notice is a big jump in the porosity to higher values, and what's going on there is because this is a high clay portion of the reservoir. We see that the neutron log is reading quite high porosity levels, which is resulting in us, I think, overestimating our porosity through this interval. But this is actually one of the things that you need to really be able to understand as a geoscientist. So let's walk through this in a bit more detail, because I feel like this is something that really separates a person who understands logs from maybe a person who doesn't understand logs that well. So once again, we're going to flip back to our density porosity because that's a bit easier to understand right off the bat. So we look at our density porosity. We've set our matrix value at around 2.65. We do that calculation, and we do a correction from effective to total, and we see that we're getting a total porosity of maybe around 14%, effective porosity of around 15% in the best part of the sand here. Now, when we go to a neutron density porosity in that same interval, now we see effective porosities of around 13 to 14% and total porosities of around 17%. So significantly higher. And we're also seeing much less contrast, between our shaly intervals and our cleaner intervals. And if we ask ourselves what's going on here, what's the driver for that? Well, the answer is really that, here in our shaly intervals, we see quite high neutron values, so on the order of 26, 27% porosity. And what's going on here is we have, this part of the depositional system, we have a lot of shells, a lot of clays, which means that we have a lot of non-movable bound water in those shells, so the neutron is reading quite high, whereas in the sands, we're reading slightly lower values, actually, according to the neutron log, and that's because that is a cleaner interval. It's predominantly quartz mineralogy, and what the neutron is reading there is actually the fluid-filled pore space, as opposed to hydrogen that's either in bound water in your clays. So that probably tells us that for this system, our density porosity is probably giving us a more accurate reflection of what is reservoir that is capable of flowing both water and hydrocarbon. And so, you know, we would want to make that change. Now what this means is it means that not only are sands are just visibly more prominent in this interpretation, but it also means if you were to go through and do something like an average porosity over this interval, you would see quite a difference between the methods. And if you had, you know, two interpreters that applied, different methodologies, you know, you may have vastly different answers with respect to things like how much oil and gas is in place, you know, maybe what the recovery factors from existing wells are, etc. So it's important to be able to come in here and understand that it's like, hey, okay, my gamma ray is telling me this is clean. I'm seeing a convergence between my neutron and density curves, which is telling me this is a lower shale part of the system. I look at the shalier intervals here, and I'm seeing, you know, significantly higher neutron values, which is, you know, telling me that the neutron log is being heavily influenced by lithology, and so maybe, you know, I don't want to incorporate that into my porosity interpretation. So those are just some of the considerations when you're doing this type of a calculation. But in general, that is, you know, there are not a lot of parameters that you set when you are doing a porosity calculation in most softwares, which both makes porosity an easy property to calculate, but it's also one where you need to be very careful with the method selection and the parameters that you are setting, because they are so crucial to how you would make that final interpretation. Okay, well, I hope this video has been somewhat useful to you. We're going to be putting out more content as part of our student competition and as part of the general Danomics learning program. So just stay tuned, and there will be more coming out soon. Thanks. Goodbye.